Welcome to this video about using the LISem model. Today we're going to use the LISem model to do some physically based simulation of landslide runout. The model itself can do many more processes related to hydrology, flooding, erosion and much more processes. Today we'll look at a pre-built dataset that you can run and see a landslide runout prediction. Before we start, I'd like to emphasize the nature of physically based modeling for natural hazards. Because of errors in the input data, model assumptions and processes, this can lead to large uncertainties in model outcomes. The model outputs must be taken in light of these uncertainties and the developing nature of physically based models. Interpretation by someone who understands the underlying physics is key for appropriate application of such modeling. So let's get started. On the left we have our interface window and on the right we have our data viewer. As you can see, there is a tab called Model. If I click on this, I get a familiar interface for the users of LISem in the past. Here you can set the input data, set the time, set the duration of the event, set the rainfall input, set the output maps, and many more things. Let's go through this. First we have the time. In this case, we're looking at a landslide runout event, and most of these are preset already, but we start with a time of 0 and we end with a time of 60. Now the meaning of these variables can usually be found by hovering over the text and getting the pop-up window. So the starting time here is in minutes, and the same is true for the ending time. So we have 1 hour of simulated time. The time step is in seconds, and since we have a grid cell size in our data for 10 meter, we have a time step of 2.5 meters, which should work fine. Time step flow, this is the actual time step, the iterative time step that's used within the normal time step to solve the flow processes. Because flow processes tend to be much quicker, this time step also has to be much slower. So this is why we use 1/25th of a time step. The time input directory. This is the directory where LISem will try to find any time series data that is needed. In this case, that is the rainfall. I actually have a rainfall file opened in the script editor. As you can see, the format is pretty straightforward. We have one line with a description, we have the number of columns, which is 2, a description for each column. In this case, the first column is the time in minutes, the second is the rainfall in millimeter per hour. Note that the LISem model always assumes that the first column is time in minutes, and the other columns are the intensity in millimeters per hour. So the description of the columns do not matter for the interpretation that LISem gives to the file. But you can have more than one rainfall station and therefore more than one rainfall column. For now we work with one rainfall value for the entire area. This is just an example, this is not the one that's used in the simulation. And you can see that we have the column with the time running from 0 to 275 and then the rainfall intensity. To make sure that at the end we have 0 rainfall, I put another value with a very high value for the time and 0 for the rainfall. So after the 275 minute mark, a value of 0 is given to the rainfall intensity. Now one of the first things to really set when you start to use the LISem model is the processes. So here you can select which processes are active during the simulation. In our case, we're just looking at runout for a certain mixture of solids and fluids. So we include initial water and initial solids. If you want to include processes related to hydrology, you select that process, and you can even include then further processes related to groundwater flow, stuff like that. Note that the more processes you activate, the more input data is required. The more uncertainties are there, and the more setup is also required. In this case, the setup is fairly simple because we only need a couple of maps to actually do this modeling. Now in the compute settings, we can select if you want to use the GPU or the CPU for the processing. Not all of the GPUs support the complex code from the LISem model. If you have a professional grade GPU, generally this will work. For the consumer cards, most of the time we have pretty good experiences, but in some cases you get an error, then unfortunately you have to use the CPU instead. There's some other options here, but for those that are interested, I leave you to the website where this is explained in more detail. Okay, so we have to set some further things. We have activated the processes we need, we set some directories and some times. Let's look at some other things. So for the time input, we don't have any rainfall active at the moment, so we don't actually need a file but if we had, we can select it here. The input maps, there are some that are required at the moment, such as the elevation model. I can load a map here. The format doesn't matter. It could be .map, could be .tif, it could be any format supported by the GDAL library. And the button next to it is actually for opening this map directly in the viewer window. So if I click this, you see we directly get the data there. The second map we need is Manning's N. This is a surface roughness coefficient, typical for flow and flood modeling. There's also a calibration coefficient there. The calibration coefficient is used to multiply every value in the map directly when it loads it. Typically this value at the start are 1. You can change these to do a quick and easy calibration of your model. So if you want to try to change the input values very quickly and estimate what would be good for a decent simulation. And finally, under boundary conditions, we can find our initial and fluid and initial solid volume. Because we also have solids, we have to specify the density of those, the internal friction angle, and the effective rock size of those. Again, I have some calibration parameters preset. In the output tab, we can select what kind of output we want. LISem by default generates after each time step a variety of maps, such as the flow height, the solid height, the flow velocities, the peak heights, the peak discharges, etc. If you want more detailed output, you can select the output time series option and even select the frequency at which you want this output. Make sure that you don't output too often and output all the variables, because this will quickly fill up your hard drive. Finally, in the simulation stats, you can see some hydrological properties, such as the area, the rainfall, the flow, the total flow in your area, the infiltration, etc. So a sort of overview of the water balance and the discharge for each outlet. Okay, so we set all the things we need to set, and I can actually start to press run on the simulation. So on the top here we have 3 buttons, the run, the pause, and the stop button. If I press the run button, the simulation will start. Directly you can see that several layers are added to the map viewer. The hill shade is placed underneath. Then, since we have two-phase flow, there's a two-phase flow layer with a two-dimensional color legend. So the blue shades are water, and the more red is in there, the more solids are there. So you can see that we have quite a bit of solids in there. And the velocity is overlaid, and the direction of those and the magnitude are indicated as arrows. So we can see the landslide actually running out from the top of the hill, the release area, to the deposition area. If you want to select any other variables you want to use, this can be done. There is a user map which you can activate, and you can select which variable you want to see. So for example, the internal friction angle could be something, but that's typically what you input. The solid height, the velocity at that moment, the drag coefficient, etc., etc. Based on the processes that you activate, there can be more or fewer parameters available here. Okay, so this has pretty much deposited. The velocities have gone to 0, so I will stop the simulation now. And we can have a look at the output of the model. So if you go to the result folder, where all the results have been stored, we can start to look a bit at what's there. There's a couple maps related to the flow heights. So for example, we have our maximum fluid height, HF max, our maximum solid height, HS max, and note that these do not necessarily occur at the same time. So the actual total flow height is not the same as the maximum solid height plus the maximum fluid height. For that, you can output a time series and do analysis on that yourself in more detail if you want. We also have the final solid height, so the deposits, and the final water height. In this case, the mixture is quite has a high drag coefficient, so they move pretty much together. So you see that they deposit also at the same location. Then we can get some information about the total fluxes, the peak fluxes, the maximum solid concentration, the velocities near the end, and we see that the main body of the landslide has lost its velocity there. the maximum velocity, which goes up to quite high values, but again, landslides run out, so that's quite typical. The final solid velocities, which are pretty similar to the final fluid velocities because it's such a mixture that moves together. So this is some of the output that is typically there. We also have a total.txt file, which shows you also the information, the hydrological information. In our case, this is not such an interesting file at the moment because we only had initial water volumes. So that was what we see in the surface flow column. Total surface flow, which is the millimeter average for your entire area. It's not so meaningful for landslide simulation. And finally, the hydrograph, but we don't have an outlet set at the moment. But if we had, there would be a hydrograph in the hydro.csv file. So this is an example of running a simulation. Now, for many users, running a simulation is meaningless without good calibration. We want to be able to be sure about the quality of our model and validate the actual work. Well, in the data set that's provided together with this video, there's actually some means of calibration provided. If you go to the maps folder that's together joined with the data set, you can also find a inventory. So that's an actual observation about the deposition location. It's called ac_impact.map. And here you can see the actual extent of landslide flow impact. So we can compare this to our model results. So let's see if the crude initial calibration that I did was any good at all. Let's say we look at the maximum solid height. It should be a pretty good representation. So if we overlay them, we can see pretty well that, well, we did reasonably well for a landslide runout simulation. It's pretty average in terms of quality. Of course, in reality, you will want to give a more objective number to this, but for this means of this video, we'll keep it at that. So the next step usually, once we have a means of providing an actual number to the quality of our simulation, we want to do some kind of calibration. And we can do that pretty easily with the scripting interface. I will close for now the rainfall file and the total file, and I will make a new script. And within this script, what we can do is we can do an automated calibration with the LISem model based on the inventory of the landslide runout extent that we have. I will save this first as calibration.script, and I will paste now the following code. I will take you through what the actual meaning of this code is. You can also find this script on the LISem website. So as usually, we start with the function main. Void main is always the entry point of the script. When we start a script, we go there. Now there's some comments explaining what is done. But the optimize custom function is a built-in function that does gradient descent optimization. So it tries to find the minimum error based off a function that you provide. In this case, that's the calibrate function. The calibrate function takes some parameters, a list of numbers, which represents the parameters for the model, and it returns an error value. And the optimize custom function is going to try to minimize that error. Now, the way that this works might be nice to explain a little bit. There are several types of calibration that you can do. So one of these types is what's called brute force. So imagine we have a function, and this function depends on the parameter value, and it gives us back our error. So for landslide modeling, we could imagine that we have our internal friction angle parameter, which is a parameter that's specific to the material in the model. And based on the value of that, we get an error. And perhaps our error is, if our error is 0, we have a perfect simulation. If our error is 1, we have a very poor quality simulation. Now, our target, of course, is to find the minimum in the error. We want to find the lowest error simulation that we can. And then in the second stage, we can validate the model based on some unseen before validation data. To do this, what we can do is we can say, let's brute force this problem. Let's just sample at regular intervals and try many different combinations of parameter values. So in this case, we sample 7 different values, 6 different values. And at each of these locations, we find the error value and we keep track of which is the lowest one. and then this would be our best parameter value. You can imagine sampling more of these points would have a benefit for finding a better simulation. You might get closer to the actual minimum. The downside is, especially if you have many different parameters, not one, but 2, 3, or 4, there tends to be many parameter combinations that you can attempt. And this quickly goes exponentially into the millions. And we cannot run a million simulations because of time limitations. So there are smarter methods to find an optimal simulation. So another approach is called gradient descent. In a one-dimensional example, so where we have one parameter, gradient descent works by starting at a random point and then looking at the gradient of your error function. And it does this by taking a very small step to the left and to the right of the current location, finding the slope, and then moving down slope. And based on some intelligent estimate of the steps, it's going to go down slope and try to end up in a minimum. Now what you might note here is that this minimum might be the total, the global minimum, or a local minimum. So it's important to try multiple starting values and end up hopefully in the actual global minimum. These methods can also be combined. Brute force might be combined with gradient descent to give you better starting positions. So that's a bit about the different methods. Both of these can be done very easily within the LISem scripting interface. In our current example, we use gradient descent because it's a bit faster. So let's go back to the script. We have our optimized custom, which does the gradient descent, and the function that we're going to calibrate is called calibrate. We have two parameters. We provide their initial value in a list. They start out both with a value of 1. Note, this doesn't mean that the internal friction angle is 1. We're going to use it as a multiplier for the internal friction angle. And here I indicate both of them has to be positive. Internal friction angle can be positive only, and the same is true for cohesion, which is the other parameter that we put into the model. So, the calibrate function. This function has to run the model, determine the error value of the model compared to observations, and then return that error value. Let's see how we do that. The first thing we do is we run the model. And for that we have the built-in function run model. It takes a run file and then two options. There's a specific way in which you can provide the options, which is explained also in the script. In this case, we're going to provide the internal friction angle calibration multiplier. So the internal friction angle map is multiplied by that value when we load it. And as such, 1 is a good starting value because that means we start with the original data that's in the map. After we run the model, we actually load the impact map, which is the, well, in this case it tries to read the factor of safety, which is not the one we're interested in. We're interested in the maximum solid height, HS max.map. So if you go to our result folder, that's this one, which contains the actual maximum solid height. And the inventory that we're going to load is actually in maps, and it's called AC underscore impact map. So with these two maps we can actually do a comparison. Now there's many different ways to do a comparison and give a number to this. One of them is percentage accuracy, another is the Cohen's kappa, another one is Pearson correlation, area under curve, region under curve. There's many alternatives to this. For me now we use the continuous Cohen's kappa, which is an extension of the normal Cohen's kappa. And the reason we use the continuous version of it is because we need a continuous function to work with the gradient descent. Typically if you use Cohen's kappa or some other metric based on individual pixels that say yes or no, and we do that in this case, our model says yes or no landslide and our observations say yes or no landslide. The function, the error function itself is not continuous because it depends on discrete pixels. And the continuous Cohen's kappa function is a continuous extension of that. So that allows us to do the gradient descent calibration. So we calculate the error value by map continuous Cohen's kappa. We print some values related to which simulation we have done. And finally, we return the error value. Now note, I do not return error value itself, but one minus. And that's actually because the Cohen's kappa in itself is not an error value, it's an accuracy metric. So the higher Cohen's kappa is, the more accurate your model. And we have our optimization function, which tries to find a minimum. So we want to find a minimum, which means we want to minimize the error. So we have to define some function that is an actual error indication of the model. And since we only have an accuracy metric, we can flip the whole thing by saying, okay, instead we provide 1 minus the accuracy, which is the error. So we have a minimum in 1 minus the Cohen's kappa. We have a maximum in Cohen's kappa itself. And that should give us a maximum accuracy for our simulation. Okay, so that's a little bit about how the script works. You don't need to know all this, of course. You can simply copy and change some of the values that you find interesting, such as changing the parameters that you want to use, changing the comparison. You can compare not only with inventory, but also with discharge data if you want. You can compare many different observations to do a calibration. So let me save this and actually run the script. And we see that the script will automatically go on and on. By default, Optimize Custom uses 200 iterations, and for each iteration it actually needs to sample the error function 4 times. So there will be 800 simulations before it's done. Typically you don't have to wait that long, but that's a detail for later. So for now we can see that the simulation has started. It's actually updating the output here. And when the simulation is done, the script is automatically going to estimate the error, and after that it's going to update the input parameter values to find the minimum in the error. So you might be wondering, at what point can I safely stop the algorithm? Well, there's a couple ways to determine this. The first one is to say I have a limit in my computation time, so I simply stop it when I don't have time anymore. Well, that's not always the best option. A second option is a bit more intelligent, is to say, when does my algorithm converge? So what do I mean by this? We see that the input parameter values are going to change, and as soon as we see the iterations progress, we're going to get closer and closer to our final value. At the end of the process, we see that the steps that are taken become smaller and smaller, and we can say after a certain time, when the steps that are being taken are so small, we've reached convergence. And this is something to look for in the output from the script, because from the output from the script we can actually check what are the accuracy values from each iteration to iteration, and if we see that the changes there are sufficiently small, we can assume that the algorithm is not going to go anywhere else anymore, and that any changes that are going to occur to the parameters can be ignored safely. I want to thank you for watching this video about the LISem model. I hope you found it useful, and as always you can check the LISem website for more information. The data and the script that I've used in this video are also uploaded and linked in the description. Thank you very much.